By the end of the 1800s, physicists really thought they kind of had things wrapped up. Newton's laws of motion were incredibly successful at describing motion, and energy, mechanical energy, had been successfully sort of united with thermal energy. In the 1800s, Faraday and Maxwell and others had really wrapped up electromagnetic theory, and physicists really thought that there was a few little odds and ends that people hadn't quite sorted out, but folks really thought that they just about had it wrapped up. People that should have known better were writing things like, is this the end of science as we know it? Are we about to figure it all out? Well, of course, they were completely wrong. They were not about to figure it all out. In fact, those few little tiny corners that they hadn't figured out ended up being an enormous can of worms, which, when opened up, revealed aspects of the universe that are just mind-blowing. So one of those theories is relativity, and we talked a little bit about that in the last chapter. There's really two pillars to modern physics, or 20th century physics, this revolution in science that happened right around and shortly after the turn of the century, the beginning of the 20th century. And the one pillar is relativity. So the special theory of relativity, what we learned about in the last chapter, deals with situations where things are moving very quickly. The general theory of relativity deals with the very massive. It talks about how mass can bend space-time around it. It's a theory of gravity that involves the bending of space-time by mass. And it's incredibly successful. So that deals with the very big and the very fast. What we're going to learn about in this chapter is quantum mechanics, which deals with the very small, the very tiny. What happens when we really, really try and understand these subatomic particles, when we really try and understand the nature of the atom? That's what we're going to learn about in this chapter. It's called quantum physics. A lot of people think quantum means like high tech. In industry, they use quantum to just mean like fancy or the future. But no, what quantum really means is quantized, which means it comes in discrete packages, like a photon. We're going to talk more about that as we go along. So these two theories, as strange as they are, as much as they seem to contradict our common sense about how the world should work, they are incredibly, incredibly successful. The electronics in your cell phone would have never been invented had we not discovered the quantum theory. Your GPS just straight up would not work had we not discovered relativity. In fact, if you tried to run a GPS system, a global positioning system, on Newtonian mechanics, on classical physics, it just wouldn't work. In fact, in just one day, your GPS would be off by like 100 meters, and then an additional 100 meters the next day. So it would really just not work at all. So these two theories are incredibly successful. And in particular, quantum physics, even though you've probably never really learned about it, it is everywhere. It plays into the design of all of our electronic devices, which, there you go, that's everywhere, right? So these are two incredibly successful theories of physics that you maybe have never learned about. Let's dive in. Let's talk a little bit more about what quantum physics is. So the goal of this chapter is to understand the quantization of energy for light and matter. The quantization of energy. We're going to spend this whole chapter talking about that. But what that means is that the energy comes in packages. In other words, it's not continuous. An analogy I sometimes use, and it's a bit of a stretch, is that soda in 12-ounce cans is quantized. You can either get 12 ounces of soda or 24 ounces of soda or 36 ounces, but you cannot get 14.8 ounces of soda if all you have are cans of soda. The soda from the drinking fountain, or from the soda fountain, that is continuous or not quantized. I can get however much soda I want out of that soda fountain. So that's an analogy that I'll use again as we go through here. But again, we're going to spend this whole chapter talking about what this idea of quantization of energy means. It is a very surprising idea. So much as we started relativity just with this simple, not really pretty simple idea that the speed of light is the same for all observers. And then we kind of just took that out and we saw, well, what conclusions can we reach from that? Well, in much the same way, we're going to start with this idea of the quantization of energy And we're going to see where that leads us. It turns out it is also going to lead us to some very surprising things. This is kind of a loose roadmap of where we're going to head in this chapter. Waves behave like particles. We've actually already talked about this, right? We've talked about the photon model of light. And in the photon model of light, we treat light like a little particle. We're going to go into that in a little bit more detail in this chapter, and we're going to talk about the evidence for that. Like, why is it that we actually believe this is true, and not just some intellectual trick that we're playing? And we're going to find that just as waves behave like particles, very surprisingly, particles also behave like waves. And so, where we can see these diffraction patterns, like we learned about for the double slit diffraction pattern and the diffraction grating pattern, that type of thing, we're going to find that that same exact thing happens with particles, which is a little bit surprising. And so finally, we're going to talk about how these things, the wave-like nature of particles and the particle-like nature of waves, we're going to talk about how the quantization of energy plays into that to reveal some very, very surprising results. And ultimately, in the next chapter, or sort of our destination here, is we're going to see how the quantization of energy and the wave-like nature of particles gives rise to the structure of the atom. So maybe you've had a chemistry class, and you've learned about all the energy levels, and you've learned about the sp, d, f orbitals, and you've learned all the rules for how the electrons combine with each other. Maybe you've learned that, maybe you haven't. I know that when I first took chemistry, it just felt like a bunch of arbitrary rules that I had to memorize. And yeah, sure, I could memorize them. I could repeat them on the exam and get my grade. But it wasn't until I learned about quantum mechanics that it all made sense. It's like, oh, that's why the electrons exist in energy levels. That's why there isn't the n equals 1.5 energy level. So, hopefully, this chapter and the next one will tie a lot of things together if you've had some chemistry classes and you've kind of wondered, why do all these rules exist? Okay, so we're going to start our journey by trying to understand the very first evidence that really and truly light acts like a particle. So this is the very first evidence for the photon model of light, the particle model of light. And it turns out that describing this is what won Einstein the Nobel Prize. Einstein was never fully convinced during his life of the reality of quantum mechanics. He always was a little bit skeptical. And so there's certainly some irony that he won the Nobel Prize for one of the original experiments that convinced people of the validity of quantum mechanics. And so to be clear, Einstein was not an experimentalist. This was an experiment that other people had done. But what Einstein did is he came up with a suitable explanation. Other folks had done this experiment, but had really not understood why they were getting the results they got. And what Einstein did is he came along and he said, okay, well, I've got a complete explanation for this that totally makes sense and is consistent with everything else. And so let's dive in. Okay, so this is the photoelectric effect. And it's a super important experiment, again, because it is the first conclusive proof that yes, absolutely, without a doubt, light is a particle. And it takes a little bit, we have to spend a little bit of time to understand the experimental apparatus so that we can understand the results and understand the explanation that Einstein gave for it. Sort of the first very simple version of the photoelectric effect looks like this. I can take an electroscope, and an electroscope is just a metal device, and it's got these pieces of foil down here at the bottom. And basically, a charged electroscope makes these pieces of foil repel each other. But when the electroscope is uncharged, then we see that these pieces of foil hang straight down. And so the electroscope basically allows us to observe the presence of a charge. And what we'll find, and it's a little bit surprising, is that if I charge up an electroscope, if I give it a nice negative charge, then we see like charges repelling, as always. These like charges repel each other, and so we see that these leaves are pushed apart. What we find is that we can shine some UV light onto this electroscope, and we can discharge the electroscope. In other words, we can use light to discharge the electroscope? Well, we know that negative charge is carried on electrons, and so that means that there are literally electrons being ejected from this piece of metal. So I'm using light to knock electrons out of a piece of metal. And really, that is the fundamental idea of the photoelectric effect. But we find that we get some surprising things. Not just any light will do this. In fact, notice we have said specifically that UV light discharges this. It turns out that visible light will not. Why not? Because visible light has a longer wavelength and a lower frequency. Therefore, it has lower energy photons. Lower energy photons, according to this equation, which we learned a few chapters ago. And so the visible light has lower energy photons, and they just don't have enough energy to knock these electrons off. Okay, this is a modern understanding, right? This was a very puzzling experiment for the folks that were performing this at the beginning of the 20th century. And is really very puzzling without the photon model. So this is the beginnings, but then folks tried to experiment with this a little bit more, right? So this is a surprising result. So folks came up with a little bit more sophisticated apparatus to try and understand this. And so this is the apparatus, and it's a little bit tricky, but this is the experimental apparatus that we have to wrap our brains around in order to fully understand why Einstein's explanation for this is so profound. Here's the setup. We have here a tube. So this is a vacuum tube. There's nothing in here. It's a complete vacuum. It's empty of air and everything. And we hook this up to some battery, and we've got an ammeter here so we can read current. Now, with just that setup hooked up to the battery, notice this is a vacuum in here, right? So if we don't have any light shining in, as the schematic shows light, but imagine that we don't have any light here, then we have no current. Why? Because these two electrodes are not connected. Okay, we call the anode the positive, and we call the cathode the negative. It's not super important. That's not something you need to memorize, but that is what we call them. And so, again, there's no way for electrons to travel between the cathode and the anode with no light shining, because there's no wire connecting them. This is just empty air. There's nothing. We might get a tiny current right when we switch the apparatus on, because you can see this looks like a capacitor. So we might charge up that capacitor, but that'll just take a second. And once it's charged up, then no current flows whatsoever. Okay, that's the setup. One other thing I guess I should point out here is this diagram shows electrons, and remember that we define current as the flow of positive charge. So if we get this thing going, we're going to get a current flowing in the counterclockwise sense, which means that there will be electrons flowing in the clockwise sense. But again, no light, no current, because there's no way that there's no charge carriers to flow between the cathode and the anode. However, what we find is that if we shine light on this cathode, then that light will knock electrons off. Those electrons now fill this vacuum, and they'll get pulled to the positive plate, right? They can get pulled to this positive plate. And if they do that, then we can read a current. Okay, that's fine. We see some very surprising things. Let's imagine, first of all, that we're shining this light in on this cathode, and we are varying the frequency of the light, varying the wavelength of the light. What we find is that for very low frequencies, we get no current at all. It's not like a small current, it's just no current, right? Even though I'm shining light here, we still get no current. However, at some point, a threshold frequency is reached, and then presto, we start to get a current. So again, low frequency light, no current. High frequency light, the current turns on. That's interesting. The other thing we see is that we can vary the voltage here across the cathode and the anode, where a positive delta V indicates that this anode here is positive, and so it's really trying to attract these electrons. However, I could adjust this battery so that it's actually a negative potential, and then notice then that this would be negative. My electrons, of course, are negative. And so this negative electrode here then would be creating a repulsive force on these electrons. Okay, so what we also find then is that there is some negative value for this potential, where the current completely stops. As we increase the potential, we get more current. That makes sense. More current, until we reach a certain point, and then increasing the potential more does not change the current at all. However, what we do see is that weak light creates a smaller current, and bright light creates a larger current. Of course, this assumes, if we're getting any current at all, that we are above the threshold frequency. Okay, so this is the experimental apparatus. And I'm telling you, in the beginning of the 20th century, nobody could explain this. It doesn't make any sense if this light is a wave, right? I would expect that if this light is a wave, just a pure continuous wave, then even if I had low frequency light, eventually it would knock an electron or two off. It might take a little longer. I would get a lower current. But I would get a handful of electrons, not just zero. That's very surprising. It's very surprising. So, what can we learn from this? What was Einstein's explanation for this? Well, his explanation was that light comes in packages, discrete packages called photons. And these photons have a specific amount of energy. In other words, the energy is quantized. That's what we mean by that word. It's quantized. It comes in a discrete package. In that package, the size of that package depends upon the frequency, according to this equation right here. So E equals HF. That is how much energy is in a single photon, a single package of light, a single particle of light. This is the quantization of energy in the form of electromagnetic radiation. So, Einstein proposed this idea, right? Light comes in discrete packages. Well, what does that mean? It means that each photon is knocking a single electron off of the cathode. Now, how does changing the voltage, how do we get this right here, this graph right here, from changing the voltage? Well, with no voltage at all, these electrons get knocked off and they're going in random directions. Randomly, some of them will reach the anode, and so I will get a very small current. Again, with no voltage at all, I get a small current. If I have a voltage greater than 0, well, then that's going to attract the electrons to the anode. And once I've gotten this high enough that it's attracting all of the electrons, well, then increasing the voltage more does not increase the current at all. And so we see here, once we're collecting all the electrons somewhere in here, increasing the voltage does not get us any more current. Now, if I change the voltage to negative, if I reverse the voltage so that this plate is negative, well, then that's repelling these electrons. And so only the very, very fastest of them can reach this plate. The point of doing that is it allows us to figure out what the energy of these electrons is. If they've got enough kinetic energy here, then they will eventually reach this plate. If they don't have enough kinetic energy, then they won't. What determines how much kinetic energy is enough? What the voltage is set to here. Okay, so that's the basic idea. And then explaining this was the real triumph of Einstein. So if the photon has a low frequency, it has a low energy, and it does not have enough energy to eject an electron from the metal. And so it doesn't matter how many of those photons I throw at this electron, it will never get knocked out of the atom because no one photon has enough energy to do so. It's kind of like I could throw 100 pillows at my window and it will never break, but it only takes one rock. So in other words, if I'm in low frequency range here, I can throw 100 photons and never knock a single electron out, but it only takes one high energy photon to knock an electron off. That was Einstein's real breakthrough. Again, what's remarkable about it, similar to his revelations with relativity, is he just accepted it. He said, okay, this is bizarre. I guess it's reality. What's a way to explain it? And he came up with this explanation that, again, he never completely accepted. But boy, it turns out to be very, very successful, a very successful theory. Okay, so the amount of energy that it takes to pull an electron out of a metal, well, it depends on the metal. And so the work function is the amount of energy required to remove an electron from a metal. And we see that it varies. Potassium, sodium, aluminum. Notice these guys here on the left side of the periodic table. It takes a relatively small amount of energy to eject an electron from those guys. These guys more in the center of the periodic table tends to take a little bit more to eject an electron. And so notice this is in EVs. Remember that an electron volt is a very small amount of energy. And again, this is called the work function. So the naming of this is a little bit tricky. Sometimes this gets students. But the work function is simply an amount of energy. How much energy does it take to eject an electron from a piece of metal? And so we see here that it would require a photon with greater than 2.3 electron volts to create the photoelectric effect in potassium. It would take a photon that had energy greater than 4.65 electron volts to demonstrate the photoelectric effect in copper. That's the basic idea. And why do we talk about it? It's just some random experiment from, the 1920s. The reason why we talk about it is because this is the first experiment that proves that light is a particle. So again, we've got the energy of a photon. We can then write a little equation here. Let's go back to this slide. Recall here that if I make this plate here negative, then only the electrons with the most kinetic energy will reach here. Okay, how much kinetic energy? Well, it depends on the work function, and it depends on the photon energy. So let's think about this. Thinking about conservation of energy, right? We've got some amount of energy that comes in the form of a photon, that discrete package of light that carries a discrete amount of energy. That comes in the form of a photon. That energy is absorbed by the electron. Conservation of energy tells us that energy has to go somewhere. Where does it go? The energy of the photon must equal the work function from the metal. So that's how much energy it took to remove the electron from the metal. And anything left over will be kinetic energy. And so what we can do then is we could rearrange this to get the kinetic energy by itself. And what we would end up with then is this equation right here. The maximum kinetic energy equals HF minus the work function. So in this case, this is the maximum kinetic energy. Why do we say the maximum kinetic energy? Because not every single electron in a given metal takes the exact same amount of energy to release it. In other words, the work function should be interpreted as the minimum amount of energy that's required to eject an electron. But some electrons might take a little bit more energy. So that's why this is a K max. So if the photon has enough energy greater than the work function, then an electron is emitted from the metal. But if it does not have energy greater than the work function, then it just isn't. And if that photon has more energy than the work function, then the electron will be emitted with some kinetic energy. And so that's what shows up here. Let's just do a quick example. In the photoelectric effect experiment, why does red light not cause the emission of an electron, though blue light can? Is that because the photons of red light don't have sufficient energy to inject an electron? Because the electric field of the red light oscillates too slowly to eject an electron? Because red light contains fewer photons than blue light, and there's just not enough to eject electrons? Or that the red light doesn't penetrate far enough into the metal? Why don't you think about it, and I'll see you on the other side. Okay, so let's look at this. First of all, the photons of red light don't have sufficient energy to eject an electron. That one sounds pretty good. I'm very tempted, but let's see what else we've got here. The electric field oscillates too slowly? I don't know. I'm not sure that has anything to do with anything. The red light contains fewer photons than blue, and not enough to eject electrons. Oh, that contradicts our model that we're talking about here, doesn't it, right? It's not that there's a bunch of photons coincidentally colliding with a electron. No, it's a collision between one photon and one electron. That's how we're understanding this. So that can't be it. The red light doesn't penetrate far enough into the metal? I don't think that's it either. It must be A. So it's related to the frequency, but really it's the fact that it is the size of the package. It's just not big enough. A red light photon just does not carry enough energy to knock an electron off of the metal. Let's do a numerical example. What is the maximum electron speed if sodium is illuminated with light of a wavelength 300 nanometers? The work function for sodium is 2.75 eVs. And I note here, sometimes it's useful to use Planck's constant in eV seconds. And then here's this number. Okay, so we're going to be looking for K max. And the maximum kinetic energy is going to be the energy of the photon minus the work function. Let's do a quick step of algebra in here. Recall that since the speed of light is equal to frequency times lambda, we can plug in c divided by lambda for the frequency here. And so I'm going to actually rewrite this like this. And we can just plug in our numbers. Okay, so I've plugged in my numbers. Here is h in eV seconds, the speed of light, 300 nanometers, and I'm subtracting off the work function. And so when I do that and I run my calculator, then I get 1.39 electron volts. Well, okay, so that is the maximum kinetic energy of an ejected electron. Let's figure out what the maximum speed is from that. In order to do that, I'm going to go ahead and convert this to joules. Recall that our conversion is 1.6 times 10 to the negative 19th joules in 1 eV. And so when I run my calculator there, I get 2.2 times 10 to the negative 19th. And now we're in joules. So a very tiny amount of energy. Again, remember that an EV, an electron volt, is a unit of energy. It's sort of an atomic-sized unit of energy. That's why we're going to use it a fair amount in this chapter. And now, of course, I know that the kinetic energy is 1/2 mv squared. So now I could plug in v equals the square root of 2k over m. Again, plugging in my numbers. 7 times 10 to the 5th meters per second. So that's pretty fast, right? Again, a tiny amount of energy, but the electron mass is very small. Again, this is the first experiment that proves light is a particle. That's why we're kind of spending a little bit of time on this one particular experiment. So, what are photons? Let's return to the double slit experiment, which we talked about a few chapters ago. If we use incredibly dim light, the fringes are too faint to see. So this is the Young's double slit experiment, shown here. And what do we see here? Well, it looks like just a handful of dots, doesn't it? I'm not seeing really much of a diffraction pattern. But if we send this very dim light in, just a handful of photons at a time, after a little bit longer, well, it still just looks like a bunch of dots. Maybe I'm starting to see something. I don't know. Here's a little bit longer. Ooh, now I'm definitely seeing a diffraction pattern here. And if I build it up over a very long time, I see definitely a diffraction pattern. This is the Young's double slit diffraction pattern that we've seen before, that we've seen pictures of in our book. It's interesting that it got built up just a little bit of it at a time. And so even if we send in photons, one photon at a time, we get this effect. Ooh, now that is a little bit surprising. If only one photon at a time is passing through the apparatus, it must interfere with itself to create the wave-like pattern. Each photon, despite the fact that it's a particle-like object, must somehow go through both slits. So this is super weird, right? In this particular series of images, and these are real images, this is not a graphic that somebody came up with, we're sending photons in one at a time. We see evidence of the photon-like nature of light, the particle-like nature of light, because just one spot on this paper, on this photographic paper, gets exposed at a time. Definitely evidence for the particle-like nature of light. But By the time we get down here, we're seeing evidence of the wave-like nature of light. Why? Because what exhibits diffraction patterns? Only waves, right? Waves diffract. If I throw basketballs through an opening, I'm never going to see a diffraction pattern. I just won't. Particles don't diffract. Waves diffract. So if you show me a diffraction pattern, you just showed me a wave. But look at this. We're looking at particle-like nature also. So what are we to conclude? Sometimes light exhibits particle-like behavior, and sometimes it exhibits wave-like behavior. And it gets even stranger than that. It turns out that whether these photons act like waves or like particles can depend on the experiment. So for example, in this experiment shown on the screen here, we've got the double slit experiment. And we see that even sending the photons in one at a time, we still get a diffraction pattern. And so we say, oh gosh, somehow one photon is going through both slits. Ooh, my brain doesn't really handle that very well. I'm going to set up an experiment. And folks have done this. I'm going to set up an experiment where somehow I'm going to be able to determine, did it go through slit number 1, or did it go through slit number 2? Which slit did it go through? And it turns out we can set up an experiment to where we know, did it go through slit 1 or did it go through slit 2? Guess what happens when we do that? We've got this, and we're shooting photons one at a time. And we say, oh, photon 1 went through here. Great. Photon 2 here. Photon 3 went through this slit. Okay. Guess what? At that point, we no longer see the diffraction pattern. By measuring which slit the electrons have gone through, I've confined them to one of the slits. They no longer pass through both, and my diffraction pattern goes away. It's super strange. It's super strange. But we're going to find that somehow the action of measuring influences the system itself. And it's something that is unavoidable in quantum mechanics. And there's been a lot of different ways folks have tried to wrap their brain around this. But the fact remains, no matter how you wrap your brain around it, that when we start talking about quantum mechanics, the experimenter becomes part of the experiment. Always. Which is really crazy.